In this video, we will learn about the production of the landing gear and its role in the aircraft. The manufacturing process of landing gear is a vital aspect of the aerospace industry, driven by the principles of engineering that aim to transform customer needs into. In this video, we will learn about the production of the landing gear and its role in the aircraft. The manufacturing process of landing gear is a vital aspect of the aerospace industry, driven by the principles of engineering that aim to transform customer needs into affordable and innovative solutions. Once the design is finalized, the manufacturing process commences with machining of landing gear parts. This phase involves using sophisticated and digitized industrial processes to ensure precision and accuracy in crafting critical components. Computer numerical control (CNC) machines and advanced machining techniques are employed to create parts with tight tolerances, ensuring optimal performance. After machining, the landing gear components undergo heat treatments. This process involves subjecting the materials to controlled heating and cooling cycles to enhance their mechanical properties, such as strength and durability. Heat treatments are crucial to ensuring that the landing gear can withstand the immense stresses during aircraft takeoff and landing. Surface treatments and painting come next in the manufacturing sequence. These treatments protect the landing gear from corrosion and environmental damage, ensuring a longer service life. Additionally, painting helps to enhance the landing gear's aesthetic appearance. Once all the individual components are ready, the latest generation quality checks are performed. Subassembly of landing gear components is the next step, where various parts are brought together to form subassemblies. This process streamlines the final assembly phase and ensures efficient production. The assembly of landing gear is carried out on state-of-the-art assembly lines, where skilled technicians meticulously put together all the subassemblies and components. Throughout the assembly process, in-house testing capabilities are utilized to evaluate the performance of the landing gear, simulating real-world conditions and verifying its reliability. After passing all the quality tests, the completed landing gear is ready for delivery to the customer's final assembly lines. These landing gears will be integrated into the aircraft, ensuring a crucial component is in place for safe and reliable operations. 3D woven carbon fiber and ceramic matrix composites offer unique properties that significantly improve aircraft performance and efficiency. This makes the composites key players in the aviation industry. The manufacturing of 3D woven carbon fiber composites starts with the selection of high-quality carbon fibers. These fibers are lightweight and have exceptional tensile strength. They are then woven into complex three-dimensional structures using specialized weaving machines. The 3D woven preforms allow for precise control over the fiber orientation, resulting in composites with enhanced mechanical properties in multiple directions. After weaving, the preforms undergo an impregnation process where they are infused with high-performance resins. This impregnation fills the gaps between the carbon fibers and forms a solid composite material. The composite is then cured under controlled temperature and pressure conditions to achieve optimal bonding between the fibers and the resin matrix. The resulting 3D woven carbon fiber composites exhibit high strength, stiffness, and excellent fatigue resistance. Similarly, the development of ceramic matrix composites, CMCs, involves weaving ceramic fibers into intricate three-dimensional structures. The preforms are then infiltrated with a ceramic matrix material, such as silicon carbide or silicon nitride. Afterward, they undergo consolidation processes, which typically involve high-temperature densification. The resulting CMCs boast exceptional thermal stability, high temperature resistance, and low thermal expansion coefficients. Both 3D woven carbon fiber composites and CMCs have diverse applications in the aviation industry. Structural components. These composites are used to manufacture structural components of aircraft, such as fuselage sections, wings, and tail surfaces. Their high strength-to-weight ratio allows for lighter yet robust structures, leading to improved fuel efficiency and range. Engine components. Both composites are employed in aircraft engines to create components like fan blades, shrouds, and combustor liners. Their high-temperature stability enables engines and combustor liners. Their high-temperature stability enables engines to operate at higher temperatures, enhancing fuel efficiency and performance. Thermal protection systems. CMCs are particularly valuable for thermal protection systems in spacecraft and hypersonic vehicles. Their ability to withstand extreme temperatures makes them ideal for use in heat shields. Braking systems. Carbon ceramic brake discs are used in high-performance aircraft due to their excellent heat resistance and weight reduction compared to traditional metal brakes. The manufacturing process of the Boeing 787 begins with the production of major components and subassemblies, which are fabricated by various suppliers around the world. Approximately 50% of the Boeing 787 Dreamliner's primary structure by weight is made up of composite materials, including carbon fiber reinforced polymers. To facilitate the transportation of major components from various supplier locations to the assembly facilities, Boeing employs 4 modified Boeing 747-400 aircraft, known as Dreamlifters. These massive cargo planes have an enlarged fuselage, allowing them to carry large sections of the Dreamliner, such as wings and fuselage barrels, to the final assembly sites. The fuselage sections are manufactured by multiple suppliers. Kawasaki Heavy Industries in Japan produces the forward and center fuselage sections, while Spirit Aerosystems in the United States manufactures the aft fuselage section. Alenia Aeronautica in Italy and Global Aeronautica in the United States produce the horizontal stabilizers. The vertical tail fin is manufactured by Boeing itself. The wings, a critical component of any aircraft, are co-designed and built by Mitsubishi Heavy Industries and Kawasaki Heavy Industries in Japan. These composite wings span approximately 197 feet, 60 meters, and are crucial to the Dreamliner's fuel efficiency and aerodynamic performance. At the Everett factory, the 787 Dreamliner comes to life on a state-of-the-art assembly line. Over 30,000 workers, including skilled technicians and engineers, are involved in the production process. The final assembly involves joining the fuselage sections, wings, tail, and other components together. The aircraft's electrical systems, avionics, and cabin interiors are installed during this phase. The global nature of the Dreamliner's production means that parts from different suppliers need to come together with precision and accuracy. This coordination is a complex logistical challenge, but it also enables Boeing to optimize its supply chain and ensure timely delivery of components to the final assembly line. The production rate of the Boeing 787 Dreamliner has been gradually increasing over the years. In 2019, Boeing delivered 158 Dreamliners to customers, averaging around 13 aircraft per month. The stretched 787-9, 206 feet, 63 meters long, can fly 7,635 nmi, 14,140 kilometers, 8,786 mi, with 290 passengers. Boeing's latest aircraft, the 747-8 freighter, is undergoing a series of demanding tests to ensure its safety and performance. Pilots are pushing the boundaries, subjecting the plane to extreme maneuvers that showcase its capabilities and resilience. Velocity Minimum Unstick Test. Boeing's test pilots recently conducted the velocity minimum unstick test on the 747-8 freighter. This challenging maneuver involved intentionally dragging the aircraft's tail on a runway in California to determine its lowest takeoff speed. The test required a delicate balance of force and gentleness to set the tail down smoothly after takeoff, ensuring safe operations. Ground effects testing. Ground effects play a crucial role during takeoff and landing. To assess the aerodynamic effects when the airplane is close to the ground, pilots commanded the 747-8 to hover over the runway in several sessions. This testing allowed them to verify the aircraft's stability and control and gather essential data for refining the Autoland system, simulating different flight conditions with varying weights and flap settings. Stall and recovery tests. Pilots intentionally induced stalls in the 747-8 freighter to examine its recovery capabilities. Stalls occur when the aircraft's wings lose lift due to low airspeed. However, the 747-8 demonstrated its ability to recover efficiently from stalls, ensuring safe flying in various conditions. Vibration damping and flutter testing. The flight test program also involved verifying the aircraft's ability to dampen out vibrations and mitigate flutter. Pilots intentionally excited the wing and control surfaces to evaluate how well the 747-8 can stabilize and manage vibrations. The production process of the Boeing 777 involved significant contributions from various international partners, making it the first Boeing jetliner with such a high level of global subcontracting. Companies like Mitsubishi Heavy Industries and Kawasaki Heavy Industries were responsible for manufacturing fuselage panels, while Fuji Heavy Industries, Limited, was in charge of the center wing section. Other contributors included Hawker de Havilland, which manufactured elevators, and Aerospace Technologies of Australia, responsible for the rudder. To accommodate the production of this advanced airliner, Boeing undertook significant expansion efforts at its Everett factory, investing nearly $1.5 billion to double its size and create space for 2 new assembly lines. In addition to expanding the physical infrastructure, new production methods were developed to enhance efficiency. One such innovation was the turn machine, which could rotate fuselage subassemblies by 180 degrees, providing workers with better access to upper body sections during assembly. The initial 777-200 model was launched with propulsion choices from 3 major engine manufacturers: General Electric, Pratt & Whitney, and Rolls-Royce. This allowed airlines to select engines from competing firms, with each manufacturer developing engines with a thrust class of 77,000 lbf, 340 kilonewtons, and higher, suitable for the world's largest twin jet. Building the Boeing 777 is a remarkable process that involves the craftsmanship and dedication of skilled workers. These craftsmen are passionate about aviation and take pride in creating one of the finest airplanes in the world. Their journey begins at a young age, where they show an early interest in mechanical and hands-on work. Once they join Boeing, they become part of a community of experts, including mechanics, sealers, plumbers, electricians, riggers, and functional test specialists. These individuals are not only technically proficient but also creative, akin to artists and musicians in their ability to work abstractly while handling concrete tasks. The assembly process takes place in the massive Boeing facility, which is like its own city within a city. Workers use their hands and specialized tools, such as rivet guns and drill motors, to put the airplane together meticulously. Every part, no matter how small, is vital to the final product's integrity. The craftsmen at Boeing see the airplane as a work of art, and each plane carries a piece of everyone who contributed to its construction. This sense of pride and passion drives them to ensure that the aircraft they build is of the highest quality. The Boeing 777 was designed with passenger comfort and long-range capabilities in mind. It could accommodate a 10-abreast seating layout and had a typical 3-class capacity of 301 to 368 passengers. Its impressive range of 5,240 to 8,555 nautical miles, 9,700 to 15,840 kilometers, 6,030 to 9,840 miles, made it suitable for long-haul routes. The Boeing 777 is the unparalleled leader among wide-body airliners, with over 2,149 aircraft ordered by 60-plus customers, and 1,710 already delivered as of June 2023. Emirates stands as the largest operator, boasting a fleet of 163 Boeing 777s as of 2018. When an Emirates A380 touches down in Munich, the landing gear faces the immense task of absorbing the tremendous landing weight, which can reach up to a staggering 391 metric tons. Despite the colossal weight it must handle, the landing gear performs its duty with remarkable efficiency, an everyday feat for this indispensable aircraft component. For an aircraft, the type of main landing gear system used depends on its size and, more importantly, its maximum takeoff weight. In the case of the Airbus A380, the main landing gear is divided into two categories: the body landing gear, BLG, and the wing landing gear, WLG, both of which are carefully designed to handle the aircraft's specific requirements. One interesting feature of the A380's design is the use of thrust reversers, which are only equipped on the two inboard engines. This decision was made to save weight and protect the outboard engines, which occasionally extend beyond the edges of the runway and are more susceptible to foreign object damage. The thrust reversers can only be activated on the ground and provide pilots with varying degrees of reverse thrust until the aircraft slows to speeds below 70 knots. When it comes to stopping the massive A380 after landing, the aircraft relies on powerful composite Honeywell brakes located on 16 of its 20 main landing gear wheels. These brakes are equipped with anti-skid technology, which automatically pulses them to prevent lockup and skidding when extreme pressure is applied. Additionally, the aircraft employs aerodynamic braking with 16 giant wingtop spoilers that rise to create drag and reduce lift. This reduction in lift allows more weight to be applied to the wheels, further enhancing the mechanical braking effect. Thanks to the unique design of its wings, featuring a large area, gentle sweep, and massive flaps, the A380 can achieve a landing speed that is 20 knots slower than that of a Boeing 747. This results in a gentle touchdown speed of around 130 knots, similar to some much smaller corporate jets. Commercial airlines often need to replace an aircraft's landing gear every 10 years or after a specific number of flight cycles, which can reach up to 18,000, depending on the aircraft model and regulatory requirements. Emirates, a prominent Dubai-based airline, became the trailblazer in changing the landing gear on the Airbus A380, the world's largest passenger aircraft. Before the A380's entry into service, Boeing 747 had dominated the high-capacity wide-body aircraft market. However, Airbus aimed to challenge this dominance and unveiled the A380 prototype, designated as the A3XX, in January 2005. The first A380 was delivered to Singapore Airlines in 2007, and Emirates received its first A380 in August 2008. In 2018, Emirates Engineering successfully replaced the landing gear on one of its A380s with the registration A6EDF. The A380's landing gear system comprises 5 sets, with 2 under the wings, 2 under the body of the aircraft, and 1 under the nose. The process was conducted at Emirates' state-of-the-art aircraft hangars, situated on the north side of Dubai International Airport. These spacious, fully air-conditioned facilities are designed to accommodate the massive A380, making them the largest aircraft maintenance facility in the Middle East. The Airbus A380's landing gear system consists of a total of 22 landing wheels, accompanied by the gear extension and retraction systems, brakes, and steering controls. Built to support the enormous weight of the A380 during takeoff, up to 590 tons, and landing, over 390 tons, the landing gear must withstand substantial forces. As the aircraft burns off fuel during flight, it becomes lighter upon landing. The replacement process took the Emirates engineering team 14 days of dedicated effort, with the aircraft carefully lifted on jacks throughout the process. The successful completion of this complex task marked a significant milestone for Emirates, demonstrating their engineering expertise and dedication to maintaining their A380 fleet to the highest standards. In a thrilling display of engineering prowess and aircraft capability, the Boeing 747-8 freighter recently underwent the Ultimate Rejected Takeoff (RTO) test. Loaded to its maximum takeoff weight of over 975,000 pounds and equipped with 100% worn-out brakes, this colossal machine was about to prove its ability to come to an emergency stop without the use of thrust reversers. Captain Kurt Vonning and the Boeing test and evaluation team prepared meticulously for this crucial trial. First, they installed a set of brakes worn down to the studs, replicating a worst-case scenario for a real-world rejected takeoff. As the 747-8 began its takeoff roll and accelerated to over 200 miles per hour, 320 kilometers per hour, the anticipation built up. Suddenly, at the peak of speed, Captain Vonning slammed on the brakes, subjecting the carbon brakes to immense forces. With the thrust reversers disabled, it all depended on the braking system to bring the massive aircraft to a halt. The 747-8 showcased its impressive stopping power, exceeding expectations by stopping over 700 feet, 200 meters earlier than predicted. However, stopping was only one part of the challenge. The wheels had generated tremendous heat during the process, reaching temperatures of more than 1400 degrees Celsius. Now, the brakes needed to dissipate this heat efficiently. Smoke billowed from the brakes as they glowed a bright orange, a testament to the immense energy transformation required to stop an aircraft of this size and weight. To further simulate a real-world scenario, the airplane had to wait 5 minutes before firefighters intervened. This delay ensured that the aircraft could withstand the heat without immediate assistance. Special fuse plugs in the tires were activated to deflate them before any potential explosions. Once the 5 minutes elapsed, firefighters moved in with water to cool the brakes and tires. Although the tires and brakes would need replacement, the rest of the airplane remained unscathed. This successful test demonstrated the 747-8's capability to handle the immense energy during a rejected takeoff, reassuring both the engineers and future passengers of its safety and resilience. With this crucial test completed and its results exceeding expectations, the new Boeing 747-8 continued its journey towards certification and eventual delivery. The aircraft had proven its ability to handle the most challenging scenarios, showcasing its power, reliability, and advanced engineering. The landing gear retraction test is a critical phase in the development and certification process of an aircraft like the Boeing 787 Dreamliner. This test is conducted to ensure that the landing gear system operates smoothly and safely during takeoff and landing procedures. The landing gear is a complex mechanism responsible for supporting the aircraft on the ground, and its proper functioning is vital for the safety of the passengers and crew. During the actual test, the Dreamliner is usually positioned on the ground, and a specialized team of engineers and technicians monitors the process closely. The pilot initiates the retraction process from the cockpit while the observers on the ground keep an eye on various parameters, such as hydraulic pressure, gear door movement, and gear extension timings. Throughout the test, any irregularities or deviations from expected performance are carefully noted and analyzed. Safety is of paramount importance, and the test can be stopped immediately if any significant issues arise. Engineers may then go back to the drawing board to make necessary adjustments and conduct further tests before the landing gear retraction test is repeated. Once the landing gear retraction test is successfully completed, the data gathered is thoroughly reviewed, and if the performance meets all safety and design criteria, the aircraft can move forward in its certification process. The maintenance and repair of landing gear, particularly the nose wheel, are of utmost importance for ensuring the safety and operational efficiency of an aircraft. The landing gear serves a critical role in providing stability during takeoff and landing, and it must withstand strong impacts from the runway and various flight conditions. Regular maintenance and repair of landing gear are crucial to ensure flight safety and cost effectiveness in the long run. One of the primary reasons for conducting scheduled maintenance and repair is to detect and rectify potential issues and wear in the landing gear system. Failure to identify and address these problems in a timely manner can lead to serious consequences for aircraft operations and result in unfortunate incidents. By maintaining the landing gear system in good working condition, the risk of technical malfunctions and accidents can be minimized significantly. Regular maintenance also plays a vital role in extending the lifespan of the landing gear components. Harsh conditions such as adverse weather, vibrations, and heavy loads contribute to wear and tear on mechanical parts of the landing gear. Through the maintenance process, technicians can identify early signs of damage and replace faulty components before they escalate into more significant issues. This not only saves expensive repair costs but also keeps the aircraft operating smoothly and safely. Furthermore, regular maintenance ensures the optimal performance of the aircraft. The landing gear is essential for safe and stable landings, as well as maintaining control and balance during takeoff and flight. When the landing gear operates efficiently, the aircraft can save energy, prolong its operational life, and reduce fuel consumption. This benefits not only airlines but also helps minimize the overall environmental impact of aviation. In the aviation industry, safety always takes top priority. To ensure the safety of passengers and crew, the maintenance and repair of landing gear, including the nose wheel, are of paramount importance and cannot be underestimated. A well-maintained landing gear system can save hundreds, even thousands of lives and contribute to the sustainable growth of the aviation sector. Specific data from the Aviation Safety Reporting System, ASRS, indicates that a considerable number of aviation incidents and accidents are related to landing gear malfunctions. According to a report by the Federal Aviation Administration, FAA, landing gear-related issues accounted for approximately 7% of all aircraft accidents in the past decade. Furthermore, studies conducted by leading airlines revealed that regular maintenance and timely replacement of landing gear components reduced in-scheduled maintenance events by up to 30% and resulted in an overall decrease in maintenance costs by 15%. These figures highlight the critical role of landing gear maintenance in enhancing flight safety and operational efficiency. Aircraft recycling, also known as aircraft dismantling or end-of-life management, is a crucial process that aims to efficiently and sustainably retire and dismantle old or retired aircraft. As the aviation industry continues to grow, the number of decommissioned aircraft increases, making recycling an essential practice to minimize environmental impact and reclaim valuable resources. The aircraft recycling process involves several stages, including depollution, disassembly, component harvesting, and material recovery. Approximately 85 to 90% of an aircraft's total weight can be recycled, including metals like aluminum and steel, which are among the most valuable materials recovered. For instance, a typical Boeing 747, weighing around 400,000 kilograms, can yield up to 320,000 kilograms of recyclable materials. Additionally, recycling helps reduce greenhouse gas emissions compared to manufacturing new aircraft. It is estimated that recycling a single wide-body aircraft can save up to 7,000 metric tons of CO2 emissions, contributing significantly to environmental sustainability. The aircraft recycling industry has been steadily growing, with specialized facilities and companies dedicated to this task. As of 2021, it was projected that around 600 aircraft per year would be retired, and this number is expected to increase with the continuous expansion of the aviation industry.